All right, we have a function given here of 1 plus the cube root of x minus 1, where we're restricting the part of the function that we're looking at here from where x is 2 to where x is 9. And our goal here on this problem is to find the values of c that satisfy the conclusion of the mean value theorem. Well, if we're going to do that, first we have to verify that the function satisfies the conditions of the mean value theorem. So we first establish that f, our function, is continuous. It is continuous on the interval we're working on. And we also have to establish that the function is differentiable on the open interval we're working on. And assuming this is all true, we can establish that the mean value theorem will hold true for this problem, and we can proceed to find that value of c, or values of c, that we're looking for. So how we continue from here, basically we break this up into two types of problems, one that deals with the function side and one that deals with the derivative side. On the function side, what we do is we take our values that make up our endpoints here, our x values that make up our endpoints here on our interval, we plug those into the original function. So here, if we take 9 and plug back into the original function, we'll have the cube root of 9 minus 1, so the cube root of 8, which would be 2, add on 1. F of 9 would be 3. If we plug in 2, we'd have the cube root of 2 minus 1, the cube root of 1, which is 1, add on 1, we'd have 2. We plug in the function, we get our values back, and then we find our slope based on a line that we could draw through these 2 points on our original function. So the slope of that line would be, if I simply take my results here, take 3 minus 2 and do that on top, and then take the values we plugged in to get those results of 3 and 2, take 9, subtract 2 on the bottom, our slope will be 1/7. And for the time being, we're just going to leave our slope alone. We'll come back to that here in a moment. As we transfer now over to the derivative side, we need to take the derivative of the function. If we do that, derivative of the function here, 1, would go to 0. Original function, we've got x minus 1 raised to the 1/3, so I bring down the 1/3. I've got x minus 1. Subtract 1 away from that 1/3, get negative 2/3. And don't forget to tack on the derivative of the inside quantity x minus 1, which would just be 1 in this case. If I clean up that derivative, well, since I've got a negative exponent and all of this stuff here is multiplied onto that expression with the negative exponent, I can set up a fraction where I'm going to have a denominator of 3 thanks to that fraction of 1/3, and I'm going to have my quantity of x minus 1 that had that negative exponent of negative 2/3. That'll get bumped down. I now have a positive power of 2/3. That takes care of this part and this part, meaning all that's left on top will be 1s when I multiply everything out. So what we do at this stage is we take our derivative and we set that equal to our slope, and in doing so we'll be able to find our value of c that we're looking for, which will ultimately satisfy the conclusion of the mean value theorem. So if we set those two pieces equal, 1 over 3 times that quantity of x minus 1 to the 2/3, that equals that slope of 1/7. As I set this up to solve for x, which ultimately will become my c value, we could cross multiply, or we could just look at the fact the denominators have to be the same thing. Either way, we'll get to the point where we have this as our next equation. If you're solving for x, divide the 3 over. Since ultimately this 2/3, we've got a denominator of 3 here, which means we've got a cube root what I would do to both sides at this point is I would cube both sides. That would eliminate the 3 over here. If I cube this side, well, let's see, next step I would have x minus 1 as a quantity squared now since the 3 is canceled out. That equals 7 cubed, which is 343 over 3 cubed, which is 27. To get rid of this squared stuff, take the square root of each side. As you take a square root, understand you're going to have plus or minus in the next step. But taking the square root of the squared side, x minus 1 would remain. And over here we'd have plus or minus the square root of 343 over 27, which right now I'm just going to leave that way and calculate all this out at the end. Because I know if I swing my 1 over, add that over to this side, do a little calculating. I take the positive square root of 343 over 27, get that result, and add 1 on. And then do the same thing with this negative. Take the negative square root of 343 over 27, get that result, and add 1 on. The decimal values that I end up with, I get negative 2.56 and 4.56 if I would round off to, say, 2 decimal places. Now, in terms of what our C would be, well, our C would not be both of these answers in this case because, if you recall, we're working on the interval from 2 to 9. So we can only go with values that we get as solutions over here that are on that interval. That would rule out the negative 2.56, meaning we only have one C value here of 4.56. All right, the next problem we're reviewing here is a problem where we're given this function and we're asked to find the intervals on which the function is increasing or decreasing. We're also asked to find any relative extrema. So to do this, we're going to need to find some critical numbers. To find some critical numbers, we'll first have to find the derivative. So my derivative would be f prime of x equals, I've got a product of x times that root, so derivative of x would be 1 times that root, which I'll write out as having a power 1/2, plus x times the derivative of that root. I'm going to bring down the 1/2. Got my quantity of x minus x squared. Subtract 1 away from that power I just brought down. That gives me negative 1/2. And then multiply onto this the derivative of the inside, which would be 1 minus 2x. As we look to simplify this, I'll take note of where the negative exponent is at and look to see everything that's multiplied to that expression that's got the negative exponent in it. That would be all of these pieces right here. Create a fraction out of all that stuff. I'm going to create a fraction because I have a 1/2. That denominator 2 will go on the bottom. My expression with the negative exponent, we'll bump that down to the bottom as well, make that a positive power. So that takes care of this part and this part. As far as what remains, well, we've got an x, we've got a 1, we've got a 1 minus 2x. We could multiply all that out. If I multiply all that out, I'd have x minus 2x squared. At the same time, you've got to remember to bring down the other part of this. And the other part, since I'm only multiplying part of this by 1, is going to be x minus x squared, all raised to the 1/2. Now we need to create a common denominator. Obviously, the common denominator is going to be the denominator that I have right here. So I want this over 2 times the quantity x minus x squared raised to the 1/2. But if I'm going to put that on the bottom, I also must multiply that to the top. So multiplying that to the top, you'll notice what happens. And this is how we always know that we're doing these correctly. We've got some like bases. So that should be one thing that stands out. But the other thing that stands out is if we put those like bases together and we add their exponents, Well, adding those exponents of fractions will come out to be a nice whole number. That leads us down to the next step here, where we're trying to put all this together over the common denominator of 2 times the quantity x minus x squared raised to the 1/2. If I look at the numerator that I created for this first fraction, I've got a 2 in it that I can just slide to the front. Then, as I was just saying, we've got this quantity of x minus x squared, which is now going to be to a power of 1 because we've added that 1/2 and that 1/2. So that's how we know that we're doing things correctly here, because that new power we get is going to be some sort of whole number. In the meantime, we are adding on, well, the numerator from over here, which is x minus 2x squared. And technically, I'm adding on that as a quantity, but parentheses aren't really necessary because we're adding it on anyway. As we go down now and clean this up a little bit further, well, let's see. If I distribute this 2 through and look to collect some like terms, I would have a 2x and an x I could put together, so 3x. And I would have a negative 2x squared and a negative 2x squared I could put together as negative 4x squared, all over the 2 times the quantity x minus x squared raised to the 1/2. So there is my simplified derivative finally, which I'm now going to use to help me find some critical numbers. So jumping ahead here to finding the critical numbers, basically we had a rational expression as a function. So we're taking our numerator, setting that equal to 0 over here to solve for the portion where the derivative is going to equal to 0. We've got our denominator over here set equal to 0 to figure out where the derivative does not exist. So on the derivative equals 0 side, let's factor out an x. And in factoring out an x, we would be left with as a solution x equals 0 because of the factor of x. And then the 3 minus 4x, if we set that equal to 0 and solve, let's see, subtract the 3 over, divide by negative 4, it would be 3/4. As far as the does not exist side goes, well, we can divide this 2 out. And because we have a 1/2 as a power, that means a square root. So if we square both sides, that square root goes away, leaving us with x minus x squared equals 0. Factor out an x. If you take out an x, you've got 1 minus x left, meaning we're going to have x equals 0 back again, because of this factor right here, and then from the 1 minus x factor, we're going to have 1. So it looks like our critical numbers, if we were establishing those, we'd say our critical numbers are 0, 3/4, and 1. And obviously we need those to explore where this function is increasing or decreasing. In terms of the original function that we were given, you always got to be aware with your critical numbers again, if those critical numbers are in the domain. So it would be worthwhile taking those values and plugging back in here just to check if this was a critical numbers type question. However, in exploring where this increases or decreases, having these values in play, whether they work or not for the original function, can be useful to set up our intervals to explore. So let's go to the intervals now. As we set up our intervals, we're going to explore our intervals for x. We're going to use the first derivative to help us decide where the function is going up or down. And then we're going to look at those changes in direction for the function, if there are any, to determine extrema. So we're starting at negative infinity. We are working our way up to the first critical number we found of 0. We're pausing at 0. We're going from 0 to 3/4 next. We're pausing at 3/4. We're going from 3/4 to 1. We're pausing at 1. And then we have no more critical numbers, so we go up to infinity. All right, as I consider these values of x that I found of 0, 3/4, and 1, and what's happening with the first derivative, well, where x is 0, the first derivative will not exist. We found that solution for both the equals 0 and does not exist side. So the does not exist side actually trumps the equals 0 side. 3/4 we found when the derivative equaled 0, and 1 we found when the derivative did not exist. So now to figure out our signs on our derivative, we take values on these intervals, we plug back into the derivative, the simplified form that we found way back over here. So plug into this guy. You take a number that is on the interval from -infinity to 0, so something that's basically negative, and you plug back into that derivative, you will find that you get an undefined answer. If we take a number between 0 and 3/4 and plug in, so something like 1/2, 0.5, right? If we plug that in to the derivative, we will find we get a positive result. Something between 3/4 and 1, choose 0.9 for instance. If you take 0.9, you plug into the derivative, you get something negative back. And from 1 to infinity, well, if you take something larger than 1 and plug into the derivative, you're going to find that you get an error. That will not exist. Now this all really goes back to understanding something about your domain of the original function. Had you explored the domain of the original function to start, you would find that the only portion of this chart really worth exploring is this portion right here between the blue lines that I've drawn. But if you haven't explored the domain, on these charts, all these results, even the parts that do not exist that have to do with the domain, tend to unfold anyway. But our domain for this original function is really just going to be from 0 to 1. Okay, now as far as the original function is concerned, we're trying to figure out where this function increases or decreases. It increases wherever the derivative is positive, so it increases from 0 to 3/4. It decreases wherever the first derivative is negative, so it decreases from 3/4 to 1. As far as any potential extreme points are concerned, well, as far as extreme points are concerned, we do have a change in direction here from increasing to decreasing. So when x is 3/4, we will have a point that's significant to find. So to find that point, you take 3/4, you plug back into the original function, since this has to do with the original function. And what you get back, well, let's see, I got an exact value of 3√3/16 when I plug back in. If you get a decimal approximation for that, that's acceptable as well. But the point is, since it goes from up to down, it is an extreme point, and it would be a relative maximum since it goes up to down. Now, one additional sort of side note here with regards to the domain of this function. I was talking about how really you only have to focus your attention if you know what the domain of this function is from here to here with the intervals that you're working with. But you might be wondering, you know what, if I take this 0, if I take this 1, I plug back in the function, I do get some answers back. In fact, the function values you get back if you plug those in would be 0 and 1. So 0 and 1 are included in the domain. I may have misspoken a little bit earlier by saying it was just from 0 to 1, but 0 and 1 should be included in that. The thing is, you're not going to have extreme points over here because there's no change in direction around those values. We only know that past 0 that it's increasing. We don't know what's happening up here. And as far as down here is concerned, we know it's decreasing up to this point, but we don't know what's happening over here. In fact, where these question marks are at, I shouldn't say that we don't know what's happening, we just know that the function doesn't exist, so there's really nothing to look at if we would graph out the original function to interpret all of our information here.